slides. Hopefully everybody can see that.
Yep, everything's okay.
Okay. All right, so I'll be speaking to you about some nuclear lattice simulations. So I'm going to cover quite a few topics, but I will not assume very much prior knowledge of some of the things I will talk about, so I'll try to be rather introductory from the beginning. So here's the outline. I'll talk a bit about nuclear forces and nuclear structure. Then I'll tell you about the main tool we use, that's lattice effective field theory. Then I'll tell you a story about two different interactions. Then I will speak about sort of a minimal or the essential elements of nuclear binding. Then I will focus on nuclear thermodynamics and the equation of state, the liquid-gas transition. And then I'll end up with something a little bit different that we've been doing in our lattice calculations called eigenvector continuation. So let me first start off making a connection with what Nico was talking about. So we know that there's a fundamental theory of quantum chromodynamics that describes the interactions of the quarks and the gluons. And so you can then think about your protons as being at the simplest level, two up quarks and a down quark, and your neutron as being one up quark and two down quarks. And they scatter with each other, and then you have the exchanges of quarks and antiquarks. And so you can then think of these in the long range limit as being coming from pions. But if we don't try to resolve the inner structure of the protons or the inner structure of the neutrons, and we just look at the long distance physics, so the low energy physics, then we have a description in terms of an effective field theory. So not a fundamental field theory in any sense, but an effective one, in which we have long-range forces being exchanged, being created by the exchange of pions. Okay, so that's where the term chiral comes from. In the limit that the masses of the up and the down quarks go to 0, these pions turn out to become massless. They have 0 mass in that limit, and that's what enables them to have this long-range behavior. And so the word chiral has to do with the handedness of the particles, and so when these quarks become massless, the different handedness of the particles decouple from each other, and that's why we use this term. Now, if we then take these chiral interactions, these chiral effective field theory interactions, and try to describe the many-body problem, then we can try to address sort of ab initio calculations or first principles, or if you want to call it microscopic A-body calculations. And that's the topic of my talk today. OK, so here's sort of a hierarchy. This is a nice chart that VTech has made. So you can start from the highest energy scales, mega electron volts, where the degrees of freedom I'm working in units of mega electron volts, where above, let's say, 1,000 mega electron volts, we have quarks and gluon degrees of freedom. Okay, but then you have your stable hadrons, things like the protons and the neutrons here. And then if you run down a little bit, so lattice quantum chromodynamics is a first principles method to try to describe all of this physics. Now, if you don't go to such high energies, but maybe focus on the level of about 100 MeV or so, then you can work with chiral effective field theory, as I've been telling you, where you have protons and neutrons and pions. If you scale down a bit more and restrict to maybe about at the level of, in terms of kinetic energies of maybe 30 MeV or less, then you start talking about bionuclei. And so we have our protons and neutrons, and we're trying to use things like microscopic A-body methods. And now if you go down to even lower energies, you have even a simpler description in terms of configuration interactions or density functional methods or mean field methods. And if you scale down to even lower degrees of lower energy scales, then we have an effective theory of collective modes, for example. Okay, so I'll be mostly concentrating on this region here, where we do these what are called microscopic A-body methods. So the technique I'll be using, talking to you about, is where we put these protons and neutrons on a lattice. So we take the lattice spacing to be somewhere between 1/2 to 2 Fermi. And so, as I said, we don't resolve the inner structure of the proton or the inner structure of the neutron, but we describe how the protons and neutrons interact with each other and in groups, and how they form atomic nuclei, as well as other things such as superfluids and such. And if you're interested in a review, here's a review paper from 2009. And there's also now a very nice textbook by my collaborators, by Timo Leide and Ulf Meissner on this. So here is a phase diagram of strongly interacting matter. We will come back to this a little bit later, but this is just to show you the applicability of the methods I'll be describing. So here's the density of nucleons. Okay, and so this is in nucleons per cubic Fermi. And so here is the density of the iron nucleus. Okay, is the nuclear matter density. And here is the temperature in megaelectron volts. And so lattice QCD, when you work with quarks and gluons, the fundamental degrees of freedom, you can go to essentially arbitrarily high temperatures. So that's very nice. However, there's a problem in doing calculations where you go to higher densities, though. What happens is that the simulations oscillate in sign, and so you get a Monte Carlo simulation, which uses random numbers, but you get just as strong a signal for positive as you get for negative, and they cancel out to give you an answer close to 0, and so you have a loss of precision. Now, if you change the degrees of freedom that you use to describe the system and work with protons and neutrons, you can actually go to higher densities at colder temperatures. So this is what lattice effective field theory does. So we put the protons and neutrons on the lattice, but instead of, so by using the protons and neutrons, we actually can go to higher densities than at cold temperatures than you could do when you work with quarks and gluons. And here, then, you can do things like look at the liquid-gas transition, and I'll speak exactly about this today. And you can also look at neutron superfluids and other things. But there's a limit to what you can do with this effective field theory description, because if the particles are too close together, if the protons and neutrons are too close together, then you have some overlapping of the protons and neutrons, and that's when you really have to start talking about the quarks and gluons as the degrees of freedom. Similarly, if the temperature is too high, then the protons and neutrons are colliding with too much kinetic energy, and as a result, you need to use some other description where you are able to talk about excited states of the nucleon, for example, and you probably will need to then go back to the quark and gluon degrees of freedom. Okay, but if you remain at low temperatures, at low energies, relatively low energies, then we can talk about chiral effective field theory, where we have the nucleons interacting through some sort of a potential, some interaction. And so the way we're going to describe or to organize this interaction is by counting powers of momentum, or powers of the mass of the pion. So this is the principles of power counting for a chiral effective field theory, and this was first proposed by Steve Weinberg. So we're going to count then powers of momentum, or powers of the mass of the pion as a small parameter, and that then at low energies, these interactions with the fewest powers of momentum will have the strongest contribution. So then at leading order, or no powers of momentum, then we have the exchange of a pion like this, and we have a interaction that we can then take to be a zero range interaction, or at least a short range interaction where we don't resolve the inner structure of what's going on in this vertex. So this is what we call leading order, but then beyond leading order, we have then more complicated things like the exchange of two pions, more complicated interactions like these short-range interactions. And that would be coming up next to leading order, or next to next leading order, as you heard from Nico. So now what we do is we put these interactions on a lattice, And we tune all the unknown coefficients to describe the scattering that we see in the laboratory. There's thousands of nucleon scattering data that we have. And so we try to describe the scattering phase shifts. So the phase shifts are basically trying to show you as a function of here I have the relative momentum between the nucleons, how attractive or how repulsive the interactions are. And so if the phase shifts are positive, we have an attractive interaction. If the phase shifts are negative, then we have a repulsive interaction. Okay? And so these are the 1s0, the spin singlet S wave, or the L equals 0 angular momentum. That's here. Okay? The lines are the partial wave analysis of the Nijmegen data, the experimental data, the empirical analysis. Okay? And so what I'm showing you here are the error bands that we get at next to leading order, next to next to leading order, or next to next to next to leading order, and how well it fits the empirical phase shifts. So you can see that the uncertainties get smaller as we go to higher and higher orders. And so this is how we tune the unknown coefficients to match the phase shifts. Okay? And that's how we can do that for all the different partial waves. I'm not going to go through all of these. So we can do this at a lattice spacing of 1.3 Fermis, or we can do it then at a smaller lattice spacing and get a better control, better agreement, smaller systematic errors if we have a slightly smaller lattice spacing. So we tune up these interactions then, and then we do something with it. What do we do with it? Well, we use Monte Carlo simulations, and specifically we use a technique called Euclidean time evolution or Euclidean time projection. And what you do is the following. You take the exponential of minus h tau. So this should remind you of the time evolution from the Schrodinger equation, except that with the Schrodinger equation, you will have minus I times h tau, or t. So I've removed the I, because we're not going to do real dynamics here. We're simply going to use this exponential minus h tau as a filter that will kill the high energy states of the Hamiltonian H, and will keep the lowest energy states to survive the longest. So just think about having a very high energy here. Then if I have an eigenstate of H that has a high energy, it gets a very fast exponential damping factor, and it will die away. Whereas if you have H, you have an eigenstate that has very low energy, then it will survive quite well as we take tau to be large, or relatively well compared to the others. OK, so that's what we do here. Now, let's think about the terms in H, the Hamiltonian. The Hamiltonian will have a term that will be the kinetic energy of the nucleons. So the kinetic energy of the nucleons will have the form minus del squared over 2m for each particle, for each nucleon, minus del squared over 2m. So if I put that here into the Hamiltonian, I will have a plus del squared over 2m times tau. And an operator like that, the exponential of something positive times the del squared, the derivative squared in each direction added together, that is a diffusion operator. Okay? So diffusion operators is something that takes like a delta function, some sharply peaked function, and as a function of time, it becomes a Gaussian that gets broader and broader and broader and diffuses out much more broadly. Okay? And so that diffusion process can be modeled exactly by a random walk of particles. So now you can imagine then your initial nucleons at time tau equals to 0, and we call this, by the way, Euclidean time. These nucleons then are doing a random walk in space as a function of this Euclidean time parameter tau. So you can think about just a particle moving around doing a random walk in space as a function of time. And that's describing how this exponential minus h tau works for the free part of the Hamiltonian. But there's also an interaction. And so as these particles are diffusing in space as a function of time, they also exchange pions to get the 1 pi exchange interaction. but they also have a short-range interaction like this, these things here. And so we can think of then this Euclidean time evolution in this manner, this picture that I've shown you. So if you've run across papers, and I'm sure you have, by people doing diffusion Monte Carlo or Green's function Monte Carlo, and Nico mentioned that a bit from the Argonne group. This is, in essence, how those calculations work, where you have these random walking particles. The way we do the calculation, though, is somewhat different. What we do is we use an auxiliary field. So let me try to explain how this works. So we have an interaction. We have n dagger n. So that is the n dagger n is the density operator for the nucleons at a given location, at a given site. If I square it, then I end up with a short-range contact interaction between two particles at that site. So I want to do things like, as I said, I want to do exponential of minus h tau, the exponential of things like this, where I have an interaction. So I need to do something like the exponential of minus some coupling constant over 2 times n dagger n squared. Okay, so this is my interaction, as I've just said. But I can think of this n dagger n as a real variable, okay? And I can rewrite then this function, which looks like a Gaussian function here, in terms of an integral over an extra variable, what I call an auxiliary variable, s, from minus infinity to plus infinity. But the function I'm going to integrate will be the exponential of minus 1/2 s squared, plus this linear term in s times some coupling times n dagger n. Now, you've learned how to do this integral. The way you do this integral is you say, how do I make this a perfect square? So what term do I need to complete this to make it a perfect square? And the answer is exactly this term here. Okay, so if I do this integral, I will get exactly this term here. That's what you get out at the end. But you get a factor squared of 2 pi from the integration. But that cancels the 1 over square root of 2 pi out in front here. So these two quantities are exactly equal to each other. So why is this useful? Well, up here we had a n dagger n squared, which is a 2-body interaction. Down here I have an exponential of n dagger n, which is a 1-body term. So now what I've done is, instead of the two nucleons interacting with each other, each nucleon is independent of the other and just simply interacting with this auxiliary variable s. So what we do is we have this auxiliary variable s for every point in space and time, every point on the lattice. And then the nucleons are no longer interacting with each other. They simply interact with this auxiliary field at every point in space and time. And once we integrate over all possible values of the auxiliary field, we get then an induced interaction of the nucleons, just like that. Okay. So here's a picture of what's going on here. So now the nucleons do not talk to each other. They just simply do their random walk, but they're feeling then these auxiliary variables, and they're getting then so maybe I have several different auxiliary fields for different interactions. And this way of thinking about the pions act much like the auxiliary fields as well. The only difference is that the pions will mediate some one-pion exchange interaction that has some correlations in space that will make them different. So now I can then write down this matrix of amplitudes from some initial nucleon j to some final nucleon I. I have a matrix. Let's say I have A nucleons. Then I have an A by A matrix, G sub ij. That will be a function of the auxiliary fields. And so now, to get the full amplitude, what I need to do is multiply the product. I need to multiply the single nucleon amplitudes together. And then I need to anti-symmetrize the amplitudes because these are identical nucleons. Okay? And so then I get then the determinant of G. So the anti-symmetrization is because the nucleons are fermions. So I get this determinant from the anti-symmetrization. And so what we do is we take a big supercomputer, the largest supercomputers we can get our hands on. And so we do this in various different places. We have supercomputers in Germany. We have supercomputers in the United States. We're using computers in Korea as well. And so we do these calculations where we use Monte Carlo simulations to calculate this determinant of G for many, many values of these auxiliary fields and pion fields. And so in the rest of my talk, I will show some results of what we get. OK? So I'm going to now tell you a story of two different interactions. And here's just a little viewpoint a nice viewpoint that David Dean wrote about some of our work on showing a quantum phase transition. OK, so I'll tell you the story so you don't have to read all these details, but it's about a quantum phase transition. So let me explain it this way. We have two different interactions, two different nucleon-nucleon interactions, leading order interactions in the chiral effective field theory. OK, and these two leading order interactions, A and B, have almost identical nucleon-nucleon phase shifts. We couldn't make them perfectly exactly the same because they're just leading order interactions, but they're very, very close. And you couldn't tell one from the other, really. And these two nucleons, these two leading order interactions also, they end up giving the same binding energies for the triton helium-3 and helium-4. So all of the 3 and 4 nucleon states look the same. And the two nucleon systems also look the same because the phase shifts are the same. But then we did a calculation of the binding energies for beryllium-8, carbon-12, oxygen-16, neon-20. And we found that A and B were very different from each other. They started off kind of similar, but then we found that B and A were different. In particular, that when we add the Coulomb interaction in, that B does a very pretty good job with explaining or reproducing what's seen in an experiment for the binding energies. But A was underbonding all of the heavier alpha-like nuclei here. OK? And so if you're interested in this story, we have a paper from 2016 describing exactly this. So we were kind of curious what differences there were, because we actually were hoping to use interaction A to simplify our simulations. And we thought that A and B would end up looking the same, but they did not, in fact. OK, so in order to try to figure out what the heck was going on here, we actually took a look at the one that was not working, interaction A. But we turned off the Coulomb interaction and just looked at the binding that came from the strong interactions. And so we had these numbers here. But what we did was we took the ratio of the binding energy for beryllium-8 to that of helium-4, and we got 1.997 plus or minus 0.006. Then we took the ratio of the binding energy of carbon-12 to that of helium-4, and we got 3.00 plus or minus 0.001. Then we took that for oxygen-16 to helium-4 and got 4.00 plus or minus 0.02. Then we looked at neon-20 and over the alpha particle, and we got 5.03 plus or minus 0.03. So we, as you probably can see, there was a very, very simple pattern here, 2, 3, 4, 5. And so that actually, to our surprise, suggested that we had done something we did not expect to do. We had created a Bose-Einstein condensate of alpha particles in our simulations with this interaction A. So what was going on is we had our calculations being done in a periodic box of a given size with one alpha particle with one helium-4. We had the helium-4 was in a zero momentum mode in this box. Then we did the beryllium-8 calculation, and we just simply ended up with 2 non-interacting alpha particles in the box occupying the zero momentum mode. Then with carbon-12, we had 3 of them. So basically, we were just adding up the energies together, the energies all together that way. OK, so now the question was, how did we end up getting a Bose-Einstein condensate of alpha particles? That requires that the interactions between the alpha particles are very weak. And we know the alpha-alpha interaction is quite strong. And that's actually why beryllium-8 is almost bound. So what we did then was we went and did a calculation using a technique that I won't have time to describe. So the technique is called the adiabatic projection method. So we have a paper on doing exactly this. But we did an alpha-alpha scattering calculation for interaction A and interaction B. And let me just show you what the difference is with the Coulomb interaction turned on. So the asterisks are the S-wave scattering phase shifts as a function of the laboratory energy. And interaction B with Coulomb is doing a pretty good job of describing the observed alpha-alpha interactions. But interaction A, what you can see with Coulomb turned on is actually this one right here. You can see it's almost 0. It goes up a little bit, but then it turns over and it actually becomes repulsive. Essentially, on average, it's kind of almost nothing. All right, and so this is exactly what was going on. Somehow we had made the alpha-alpha interaction different from what's observed. We somehow turned it off by using a different interaction for the nucleon-nucleon interaction. And so we scratched our heads for quite a while and tried to figure out what exactly was the difference. Okay, and so what we did was then actually let me stay on this slide while I talk about it. The difference between interaction A and interaction B, I will now tell you, is that interaction B used a short-range interaction. So we always had the 1 pi exchange, which is long range, but we also have some short-range interaction. In interaction B, we used a local short-range interaction, where the term local means that the interaction does not depend on the velocities of the particles. Okay, like the Coulomb interaction, it doesn't matter the relative momentum of the particles with each other. Okay, but for interaction A, we use purely non-local interactions, which were velocity dependent. And it turns out from this analysis that the local interactions were having an easier time in inducing an alpha-alpha interaction. And there's a very good reason for this, that the local interactions are able to make an attraction between the nucleons that are held in within the nucleons, whereas the non-local interaction has some velocity dependence, and they're more frustrated when trying to produce a residual interaction between the alpha particles. Okay, so knowing this, we realized that we could actually interpolate between the interactions A and B like this, and go from an interaction that's more like A over here to an interaction like this that's B over here with an interpolation parameter lambda that really does not change the nucleon-nucleon interaction at all, and it does not really change the 3-body, the 4-body system, but it changes the nuclei that are above A equals 8. And so what you see here is that on this side, where lambda is small, lambda equals to 0, we have an alpha gas, where the only bound nuclei are these alpha particles, as well as neutrons and tritons and helium-3 as well. But over on this side here, you cross a point at which, if you have enough nucleons, they stick together. They form a nuclear liquid droplet. Okay, and if you go a little bit further, then neon 20 becomes bound, and then you go a bit further, and oxygen 16 becomes bound. Then carbon 12. Then eventually you get to the point where beryllium 8 is bound without the Coulomb interaction. So that's a very interesting way of looking at the nucleon force. That nature is actually relatively close to this quantum phase transition between a Bose-Einstein condensate of alpha gas and a nuclear liquid. And so the fact that it lives relatively close to this quantum phase transition tells you that even though we're on this side in our physical universe, if you turn on a little bit of temperature and the density is not too high, you can see the remnants of this quantum phase transition in the excited state spectrum, and in seeing the clustering that you can see then in the excited states. Okay, so let me continue on. Having understood that there's this dependence on the local and non-local interactions, that they make some difference, we ask the question, what is the simplest, microscopic nucleon-nucleon interaction that when we do a microscopic A-body calculation, a fully first principles calculation, we do a pretty good job of describing atomic nuclei, let's say in particular the light nuclei, the medium mass nuclei, as well as neutron matter, with no more than a few % error in the energies and charge radii of these atomic nuclei. So we did this with an interaction with only 4 parameters. So this was a work led by one of my postdocs, Bingnan Liu, who's now a faculty member in China, in Beijing. So the parameters that we ended up using here were the following. The strength of the 2-nucleon S-wave interaction. So we actually took there turns out to be 2 different S-wave interactions, L equals 0, 0 angular momentum channels, okay? But we took the strength of the 2 interaction channels to be the same in this very simple analysis. And one of the parameters was how strong this interaction is. Another parameter we took was the range of the 2-nucleon interaction, okay? How far apart the nucleons can be while still interacting. And then another term we took was the strength of the 3-nucleon interaction, okay, to try to get the 3-body system correct. And these first 3 parameters were fitted to the nucleon-nucleon phase shifts, as well as the 3-body system. So these were all fitted to the A equals 3 or less body system. Then we took an extra parameter, which was going to be the range of the local part of the 2-nucleon interaction. This goes back to the fact that we realized that the local interaction was quite important for nuclear binding. And we tuned this interaction just to try to reproduce as much as possible the nuclear bindings we could see. So with those 4 parameters, 3 of which were tuned only to nucleon-nucleon phase shifts in the 3-body system, we fitted about 84 or so different nuclei. And you can see how this ended up working for the lattice predictions versus the experimental data for the nuclear bindings versus the mass number. These are for the even nuclei. And you can see for hydrogen, helium, beryllium, carbon, oxygen, neon, magnesium, silicon, sulfur, argon, calcium, it's not too bad. It's not perfect, obviously. It's not reproducing lots of interesting things like the spin orbit splittings and such, but it's getting the bulk properties of the bindings relatively well, especially given the fact that there was essentially only 1 fudge parameter we used for all of these. The rest were just fitted to the phase shifts and the 3-body system. Okay, so if you're interested in the details of this work, you can look at this paper from 2019. All right, so this was kind of curious. We were also then interested in just seeing how well things were working. And you can see we were doing pretty well with just these 4 parameters. So here are the binding energies in megaelectron volts versus the experimental. So these are the Monte Carlo errors as well as the systematic errors. Okay, so you can see these were fitted, so these are exactly right. But then what you can see is you can see the binding energies. There's no systematic real. They're pretty squarely on the experimental numbers. You can see that also the charge radii in the units of Fermi are also pretty good compared with the experiments. So you can see with 4 parameters, you can do a pretty good job of explaining all of this physics. So the nuclear force is complicated, but at its heart, it's close to something that is not so complicated in the end. Okay. And by the way, we also have a recent preprint we put out where we talk about something called hidden spin isospin symmetry. If you want to take a look, there's a preprint on exactly this, where we talk about how the large NC limit, the fact that if you take the limit of the number of colors in quantum chromodynamics to be large, you can get a lot of this physics of, for example, some of these symmetries, these approximate symmetries, come out from the large NC limit. Okay, so let me go on now and tell you a bit about something called the pinhole algorithm. And this is how we look at the structure of our nuclei by doing these simulations. Okay, so here's sort of I'll sort of give away what the technique is. In the middle of our simulation, so we had all these different Euclidean time steps, But in the middle time step, we essentially put in a brick wall where we have holes in the brick wall. And the nucleons can pass through the holes. But if they don't pass through the holes, then the amplitude goes to 0. That's the idea of the pinhole algorithm. So I'll explain how this works now. So we're going to see the structure, the nuclear structure with these pinholes. So we're going to take a nucleon density operator. So I will be for the spin, and J will be for the isospin. And so we'll have then some A dagger A. So that's my number operator for spin I and isospin J. And we're just going to multiply A of these together at different sites, different locations to get an A body density operator. And then what these colons do is they put they take all the annihilation operators and puts them at the beginning, and takes all of these creation operators and puts them at the end. And so this is a true A body operator where we annihilate a capital A nucleons, and then we create capital A nucleons at the end. And so what we do in the simulations then is we stick this A body density operator in the middle time step. We do part of the time evolution, half the time evolution in the beginning, half the time evolution at the end. And in the middle, we put in this density operator, this A body density, and it looks like this. OK, so we have the initial time, we have the final time, and as I said, in the middle, we have some brick wall. And this brick wall will give us a 0 amplitude unless the nucleons go through some little holes in the brick wall that we call the pinholes. OK, so what's nice about this is now we can do a simulation where we use Monte Carlo updates of the auxiliary fields and the pion fields, as I've been saying. But we also can do a simulation where we update the locations of these pinholes. And what's nice about this is that with the locations of the pinholes, we also know exactly where the nucleons are. And that gives us a classical distribution of the nucleons in space. So that's how we can get something like the density profile, the charge density profile, and then compare it with electron scattering data. OK, so if you're interested in the pinhole algorithm, how that all works, you can look at our paper from 2017 on this. And so you can see how it works with this very simple 4-parameter interaction that we've been talking about, this guy here, how the charge density looks like for oxygen 16. And you can see the empirical from the electron scattering. You see this is versus the radius, the charge density for oxygen 16. And you can see with the Coulomb interaction included, it's doing a pretty good job of reproducing the empirical charge density for calcium 40. It's also doing relatively well with the Coulomb introduced. There's a little bit of an excess here, suggesting that we have a little bit too high central density, but it's really only 4 parameters, so that seems like a pretty good result for this leading order calculation. OK, so what else can you do with this pinhole algorithm? Well, we can look at other correlations as well. So one thing that's close to my heart is to look at alpha clusters. So one way to look for alpha clusters is, well, the difficulty with seeing alpha clusters is that they're composed of 4 nucleons. So it's relatively hard to say where an alpha cluster is, because that depends on which 4 nucleons you're looking for, because these nucleons are all the same, right? They're overlapping with each other. So, but one way you can do this is by saying, well, to good approximation, each alpha cluster has only 1 nucleon of a given type. For example, only 1 proton with a spin up is in a given alpha cluster. So now what we can do from our A-body calculations is look for the correlations of 3 spin-up protons with each other. And so we look at various nuclei. So this is from an older paper, 2017, where we did this calculation with a relatively large lattice spacing this time. So the data was a bit coarser, this data. We looked at the correlations of 3 spin-up protons in different carbon isotopes. And so if you have 3 particles, three protons, they form the vertices of a triangle. So what we did was to collate all this data together, to gather them together, we found the largest leg of the triangle that was formed by the 3 spin-up protons. we put that leg, we scaled it such that it had a length of 1. We rescaled the triangle, so the longest leg had length 1. And then we put the leg on the x-axis, and then we flipped the this third vertex so that it was in the upper half plane with y greater than 0. So this is what it looked like. So we took the longest leg of the triangle and it made it have length 1. And then we mapped out the histogram of the vertex, the third vertex of that triangle. And this is something like what we saw here. So if you remember from high school, from simple high school geometry, if you have a circle, so let's this be the diameter of a circle, and imagine in your mind a circle with that diameter, then if the third vertex of the triangle is on the circle and the hypotenuse is the diameter, then that angle is a right angle at that vertex, okay? So you can see here, I've mapped out here sort of the circle. And so you can see that most of the weight of the histogram is beyond that circle, outside of that circle with a right triangle, telling you that we get an equilateral triangle on average for the carbon-12. Now, one thing you'll notice is that for carbon-14 and carbon-16, it's really not that different. There's only small differences in the histogram, suggesting that the sort of the alpha cluster structure, or at least the spin-up proton correlations in carbon-12, carbon-14, carbon-16 are similar to each other. Okay, and so suggesting perhaps to the extent that there's some alpha clustering in carbon-12, there's also some alpha clustering in 14 and 16. And so you can see that in this histogram. And the equilateral shape suggests that it has sort of what you might expect. Sorry, this is the acute angle. The fact that it's beyond the circle here tells you that this angle, the third vertex, is an acute angle, and there probably will be then a maximum nearby the point where you have a 60-degree angle or an equilateral triangle. Because of the lattice spacing here, the data is a bit bumpy. And there's really not a point that's exactly corresponding with the equilateral triangle with our lattice spacing here, but you can see there seems to be a peak somewhere in that vicinity. Okay, let me now go on. The other thing we can look at is we can try to do some thermodynamics with this pinhole algorithm, but a different kind of pinhole algorithm that I'll now describe. So having use the pinhole to see the structure of the nucleons, we realized that we could use the pinhole algorithm to do a sum over all possible nucleon states of the system. And that will give us a window into the thermodynamics of the system. So this is described in a paper from 2020, just quite recently. Again, this was led by my former postdoc, Bing-An Liu. And here is an artist sketch of the liquid gas phase transition at the critical point with Coulomb turned off, which then allows you to have these massive droplets form. Okay, so to do nuclear thermodynamics, what we need to do is we need to take the trace over all quantum mechanical states of the exponential of minus beta h. Okay, h is the Hamiltonian, of course, and beta is 1 over k Boltzmann times the temperature T. So this is my inverse temperature beta. Okay, this gives me my Boltzmann distribution, and I need to do the trace over all quantum mechanical states. Now, so what we're going to do here for the pinhole algorithm is, let me show you this in terms of the pictures. It's easy to understand than reading the equation. We're going to have pinholes at the beginning and at the end. But the pinholes will be correlated with each other. So this guy will be the exact same one as here. This one will be the exact same one as here. And we're going to sum over all possible locations of the pinholes and the spin and isospins as well. And this will give us then the trace over all quantum mechanical states. We can then, so this will be what is called a canonical partition function, where it's at fixed particle number, a certain number of pinholes. And we can also restrict to a certain fixed number of protons and neutrons as well. Okay, so that's how we do these calculations at non-zero temperature. And now here, the temperature, the inverse temperature beta will correspond with the amount of time that we evolved in with our the amount of time we evolve for our Euclidean time tau, because and in this way of seeing it, this beta is just like our Euclidean time. Okay. So by doing these simulations, we can then map out really interesting things, like looking at the charge density profile of oxygen 16. So here you see, we turned off the Coulomb now. This is in a periodic box of about 12 Fermi cubic box in size. We put in an oxygen 16 nucleus in it. We essentially make it an oven. We put it in the box. We turn on the temperature and see what happens. So then here's experimental data in the ground state. You can see we reproduce pretty well what we get. Remember, we turned off the Coulomb, so it's a little bit high at the center without the Coulomb. But then we turn on temperature of 3 MeV. And what we can see is we see a tail forming out here. We get a reduction in the central density. As we turn on the temperature higher, 6 MeV, 9 MeV, 12 MeV, we get a further reduction of the central density, and we get a much bigger pronounced tail. So we get things flying off. Perhaps we see alpha particles, things like that, as well as single nucleons at the higher temperatures. Okay, so we then took a look at, we're interested in the phase diagram of symmetric nuclear matter. So here is the density of nucleons as a ratio with nuclear matter density. So here is the density of an iron nucleus. And here is the temperature in megaelectron volts. And so here is the critical point where we expect the critical point to be. And here's the liquid vapor. Okay, so here's the liquid vapor phase, and here's the superfluid phase. So we're not probing that in this study here. But then here's the critical temperature here. Okay, as well as there's going to be a critical density at this point. So we're interested in all of these properties, as well as the coexistence line for liquid vapor. This coexistence line here. Okay. So here is what we found from the first principles calculations. We plot here the reduced nucleon density. Again, this is the density of nucleons divided by the density, normal nuclear matter density. Okay, so here's nuclear matter densities up here. And these were simulations done with up to 132 nucleons in various size boxes. And here you can see the isothermal lines for 10 MeV, for 11, 12 MeV, 13, 14 MeV, and so on. This is the chemical potential we get. And this is the pressure we get for 10, 11, 12, 13, 14 MeV temperature. And this line here, you can see the solid line here is giving us the liquid vapor coexistence line. And here you can see again the liquid vapor coexistence line. And at this apex here is the critical point in terms of the density chemical potential plane. You can also see it in terms of the density versus pressure plane. And so here you can see a comparison with the empirical result from heavy ion collisions. And you can see, even with this very simple interaction, this is the same interaction I've been talking to you about with those 4 very simple parameters. You would get quite good agreement with the empirical data. And so what we find is there's statistical errors and systematic errors here, that the critical temperature is about 15.8 MeV. The critical density is about 0.09 nucleons per cubic Fermi. And the critical chemical potential is minus 22 MeV. And the critical pressure is about 0.26 MeV per cubic Fermi. Okay. So then we can also take a look at clustering. So clustering is a function of density and temperature. So this is what we find. The way we look at clustering is we measure the density of nucleons raised to the 4th power. So this gives you a strong signal if we have an alpha cluster, because we have 4 nucleons in close proximity to each other, overlapping with each other. And we divide it by the average density in the box raised to the 4th power. So this is a strong signal tells you have an alpha cluster. So you can see when the density is above the critical density, 1.0, 1.6 times rho c, we can see there's almost no dependence on the temperature dependence. Okay, so you can see rather flat, where you just see an increase with increasing density, as you might expect. There's more overlapping of the nucleons. But once we go below the critical density, we see that there is then this temperature dependence. In fact, at low temperatures, we have an enhancement of this alpha clustering. And you can see how it's declining with the temperature, how it's decreasing. Okay, so you can see this temperature dependence of alpha clustering, or at least the 4-particle correlations. Maybe it's a bit much to really call this alpha clustering, but at least you see the overlapping of the nucleons at the 4-body level in this calculation. So let me now go on and tell you the last thing. Well, I don't have much time, but let me try to show you something new, which is kind of fun. This is a paper from 2018, but there are many groups now trying to use this thing that I call Eigenvector Continuation that I'll talk about now. OK, so what I'm going to suggest is that if you have a Hamiltonian matrix, a Hamiltonian that depends on a control parameter, like a coupling constant, and it depends smoothly on this coupling constant. In fact, usually it depends linearly on this coupling constant. Then even if you have a very, very large linear space, the eigenvector, the ground state of this Hamiltonian, will move very smoothly as a function of this coupling. Okay? And in fact, they trace out trajectories that essentially look like very low-dimensional objects. And let me show you how this all works. But let me just skip then to the application. If, in fact, the eigenvectors move very smoothly, then they can be approximated by linear trajectories, by linear approximations. Then, if you can study what the eigenvector is doing in one location, then we can predict what the eigenvector will be at another location just by a variational principle, by taking linear combinations of the eigenvector, because it's an approximately linear manifold. By taking linear combinations of the eigenvector at different places, you can get the eigenvector at another place far away. So that's the idea of eigenvector continuation. So let's consider then a Hamiltonian H of C, which is H0 plus CH1. And so we have our eigenvector psi j, which is a function of C with energy EJ C, like this, HC. And what we can now do is we can perform a series expansion about the point C equals to 0. So we do our Taylor series, EJ. So n is the derivative with respect to C, the nth derivative. So I have a series expansion for my energies, and I have a series expansion for my eigenvectors. Okay. So now, this is what is perturbation theory. You do a series expansion of the eigenvector. The problem is that if you encounter, this is in the complex plane, this is the real part of C, and this is the imaginary part of C. If there's a point where the function is not analytic, then this series expansion will diverge outside of this radius here. So there's a convergence region. So you can see how this may not, how this does not work very well for a very simple example here, which I called which we call the Bose-Hubbard model. So this is the Bose-Hubbard model in 3 dimensions, where we have identical bosons on a 3-dimensional cubic lattice. We have 4 bosons. We have a term here where the bosons hop from one site to another, and then we have an interaction that's simply an on-site interaction between the bosons, between pairs of bosons if they're on the same lattice site. And then we have a chemical potential, but we're going to make the chemical potential proportional to this term, this hopping term T. So mu is equal to -6T. So U is going to be the single site pairwise interaction, okay? And T will be this hopping term T over here. Now, so let me show you the data. So U, if U is positive, it's repulsive over here. If U is attractive, it's over here on the negative side. And you can see the exact energies for this 4-body system. This is the ground state energy divided by T. You can see there's a very sharp kink here that occurs that is telling you something very dramatic happens at this point. What happens is that you have a 4-body bound state that essentially collapses. And if you use now perturbation theory around C equals to 0, U over T equals to 0 at this point, you can try to approximate what's going on. It describes all of this behavior quite nicely. But you see, you do 1st-order perturbation theory, it looks like this. 2nd-order perturbation theory, it looks like that. third order perturbation theory, it never behaves like this. It doesn't do any of this correctly. Okay. So this looks very, very disheartening, not very promising. However, let me now show you that you can get the answer, this behavior, with something simpler than perturbation theory. Let's just take the Hamiltonian you get at this value of the coupling over here, at this value of the coupling over here, at this value of the coupling over here. So you just simply take three vectors, three eigenvectors at three different values of the coupling instead of the 200,000 dimensional space that we're talking about. Then for each Hamiltonian here, all of these different Hamiltonians, you project onto those three vectors, only those three vectors, and you solve them for the ground state in that three-dimensional space. And then you get this this solid line here, this black line, and you get this prediction that almost exactly maps to the exact answer. So what you see here is that with just three vectors in this 200,000 dimensional space, the ground state can be approximated by some linear combination of these three vectors. And that's the power of eigenvector continuation, that you can get this kink over here described in terms of just three vectors. And now, since I'm running out of time, I'm going to skip some of the mathematical derivation of this and just show you that you can now make a prediction, a very non-trivial prediction. For example, you can take now eigenvectors at this point with one eigenvector. You can't predict much. You can just simply get this almost flat line here. With two training vectors in this location, you do a little bit better. With three training vectors in this location, you actually do better than perturbation theory at any order. And with four training vectors, you're able to reproduce this behavior almost perfectly. With five, you do even better. So what's going on here with this eigenvector continuation is saying that there's information in these eigenvectors that tells you about this kink that's happening at a different value of the coupling. And the reason for this is that these eigenvectors are behaving analytically. It's like you are a driver that's driving a car that's an analytic function. If you need to make a turn, let's say 1 kilometer ahead, you have to start turning the car beforehand. And that's what's being detected in these small changes of the eigenvectors. And that's the magic of eigenvector continuation. OK, so now we've used this eigenvector continuation as a way of making predictions. For example, here is a calculation being done where we have a calculation of helium-4 with unknown coupling. So we take three coupling constants and letting them have arbitrary values in a three-dimensional space, and then seeing how well we can predict the exact value versus the prediction. And with eigenvector continuation, you can see the black line is exact value, so it should be they should match. You can see eigenvector continuation is spot on, doing a very good job. If you do something simpler like polynomial interpolation, it does a rather poor job. Gaussian processes does better than polynomial interpolation, but you can see eigenvector continuation is by far doing a better job than these Gaussian processes. And so that's what a lot of groups are now interested in trying to apply in their calculations. Now, what's neat is that if you go to even larger systems with 16 dimension now, if you do 16 training points in a 16-dimensional space, you can make a very good prediction using eigenvector continuation. And what you can see is that everything else fails miserably, giving ridiculous predictions on the level like 1,000 MeV binding energies for these predictions using other techniques. So this eigenvector continuation now has been used for things like an emulator for doing nucleon-nucleon scattering. We wrote a paper on the convergence technique. It's been used for many-body perturbation theory, going beyond simple perturbation theory to resum these series. And I told you some more about many-body perturbation theory. And there's also people using this as an emulator to make, essentially to accelerate by a factor of 1,000,000 times faster calculations with different values of the parameters of the nucleon-nucleon force. So let me now just wrap up and tell you, I've talked to you about things like the liquid-gas transition. I told you about a minimal interaction of the nuclear forces, about pinholes to look at densities and clustering. And And then I also talked to you about this eigenvector continuation that's now being used for different groups for uncertainty quantification as emulators for the many-body problem, scattering, and resummation methods for perturbation theory. So thank you very much for your patience and letting me speak today.
Well, thank you very much, Dean, for such a beautiful talk. I always enjoy listening to your new progresses in calculations. But I know you have a few minutes, so please, Alexis, what do you want to have you have a question?
Yes, I was wondering if what you called hi anyway, very nice talk. I very much enjoyed it. I was just wondering if there is any similarity, analogy between this eigenvector continuation and the Krylov methods of linear algebra. Or
yeah. In fact, Alexei, that's a good point. So the Krylov method is where you start off with an initial vector and you multiply by powers of h upon the initial vector, and that's the space that you use. And so in fact, eigenvector continuation was developed by thinking about how to find a better basis than the Krylov basis set. So I thought about, for example, perturbation theory. Suppose you could create the perturbative series at small couplings and use the 0th order, 1st order, 2nd order as the basis space. How fast would that converge? And that sort of was the development of eigenvector continuation.
Okay, thank you very much.
Sure.
Dean, do you have time for a couple of more questions? Or you have to
absolutely.
So why does the cluster vanishes with temperature you showed before?
Yeah. So what's going on, right? If it's hot enough, then there's more entropy in for the cluster to disintegrate, right? So it's simply the cost of disintegrating becomes less, and so it's just thinking in terms of the entropy with the temperature.
Okay, thanks.
Mm-hmm.
Let me see. Any more questions for Dean? I see we have some theories in the audience today. Well, I guess everyone is tired. Any more questions?
It's a long day.
1, 2. Alfredo, any questions? I guess not. Okay, Dean. If not, it was a great pleasure to have you at the Taste of Nuclear Physics. It was a beautiful talk, and I will post your presentation in the web page if you don't mind, so people can go through.
Sure.
Excellent. So thank you very much, everyone, for being another beautiful day of discussions. And tomorrow we have more with applied nuclear physics and astrophysics. It's the last day, but I think we have also a very beautiful program. I again thank you, everyone, and good night. Have a good sleep, and let's think about physics. All the best.